I am Dr. W.P. Gandhare from Kamlani Mahavidyalaya, Nagpur. Today we are going to discuss the next part of the oxidation and reduction, and today we are going to discuss the redox field of water and also redox potential, stability of the water. And in this we are going to see water as a oxidizing agent, water as a reducing agent, disproportionation reaction, and reaction we can also take place in the presence of atmospheric oxygen. So here how to find redox potential, and that we are going to discuss in today's presentation. So today's topic is analysis of redox cycle and redox stability field in the water. And as we know, what is how to find out the redox potential here in the next slide. So the topics which are covered here today presentation are the analysis of redox cycle, redox stability in water, water as a oxidizing agent, water as a reducing agent, stability field of water, and then disproportion in water and oxidation by atmospheric oxygen. So these are the topics that we have covered in today's presentation. And so for here, first of all, we are going to see the analysis of redox cycle. As we know, since the reduction, oxidation and reduction reaction taking place simultaneously, and by considering this reduction of one species and oxidation of other species, one has to take into account the oxidation of another species. If the metal ion undergo reduction to give solid metal, and simultaneously oxidation of a hydrogen take place giving the hydrogen ion, then the these two half reaction can be written as here shown. The two half reactions are here which are shown. So here metal ion accept electron become metal, solid metal, and here hydrogen gas is converted into aqueous H plus ion by the loss of electron. So hydrogen forming H plus ion, and this is forming solid metal. So these are the two half reactions. One undergo oxidation, other undergo reduction. As we know, loss of electron is oxidation, gain of electron is a reduction. And by using a Bornhaber cycle, the two reactions can be represented as this is the solid metal and directly converted into aqueous metal ion by the loss of electron. So here this is the Q1 amount of energy here required for converting solid to aqueous here, and this same reaction can take place in a different ways. This is the first step, solid is converted to gas, then gas is converted into gaseous metal ion by the loss of electron. So this is second step, and this is third, hydration, solvation or hydration of this metal ion into aqueous. So this is aquated metal ion, and this is the this is direct step, and this is in a three step. And similarly, in case of secondary reaction, hydrogen gas is converted directly to the aqueous H plus ion by the loss of electron, or this reaction can take place in a three different way. First, it is dissociated and forming hydrogen metal, hydrogen atom, and then it is converted into the gaseous hydrogen ion by the loss of electron, and then it is converted into hydration, undergo solvation, and forming this aquated H plus ion. So these are the two processes, and combine these two cycles we get these two separate cycles can be combined. So here metal ion, and so here is the metal, and here Q1 plus Q2 total, this is the reaction, metal ion plus hydrogen, Q is the change of energy, and this forming solid metal and H plus ion. So here this is converted into this is the direct reaction, and also we can convert this hydrogen into hydrogen atom and then hydrogen H plus ion, and like this. This is also shown, this metal solid is converted to gaseous metal, and this metal, and here aquated metal ion. So by these two processes can also be combined. This is the Bornhaber cycle for separate and also combined process. In the next slide now, by using this Bornhaber cycle, we can also write Q1 equals to, this is the that is we know that reaction can take place in a one step or can take place in several steps. So according to the first cycle, Q1 equal to delta HS plus ionization energy plus delta H. Q2 equal to half dissociation energy of hydrogen, ionization energy, and delta H of hydration. And total energy can be written as is given by Q. Suppose total is the Q, so Q2 minus Q1. So Q2 we know, and Q1 also we know. So this is the equation we obtained for this, and Q2 is given already. So by using Q2, so therefore it is possible to determine the total energy change which are taking place in the redox reaction or equation. The standard free energy change is also given by the equation. So this is the standard free energy change shown here. This is the equation in a standard state. Delta G0 equals to delta H0 minus T delta H0. As we know, delta G0 equals to delta H0 equals to Q, because as we know, in this case it is possible to determine the total energy change, and now this is the equation, and as we know that in the solution the entropy change delta H0 is negligible as compared to the enthalpy change, and so therefore enthalpy change is equal to the free energy change. So that equation we have written here, because delta is 0, so delta G0 equals to delta H0, and which is equals to Q. According to the now energy change of a reaction can be related to the standard EMF of the cell, and this is the Nernst equation, standard equation which show the relation between delta G0 and E0. So delta G0 equals NFE0, so delta G0 equals to minus NFE0 equals to Q equal to Q2 minus Q1, and E0 equals to, we can write Q1 minus Q2 upon NF. So this is the equation. E0 standard electrode potential or standard redox potential can be determined if the other thermodynamical property parameters are given. So knowing the thermodynamic parameter, it is possible to calculate the redox potential of any redox reaction using a redox cycle. Now consider example of redox reaction of zinc and copper ion in the aqueous solution. The reaction is represented as shown here. One example, this is the general how to find the redox potential by using redox cycle, and now knowing this here another example, that is the redox, consider the example of redox reaction between zinc and copper ion in aqueous solution. The reaction is shown here. So this is the zinc metal, copper ion. Zinc is converted into zinc ion, copper ion is changes to copper metal. So these are the two reactions. As we know, galvanic cell, in this case also the same reaction is taking place. So various steps involved in the reaction can be shown as here. Zinc is first converted to zinc, gaseous zinc, and energy change is shown here, positive required energy required to convert solid to gas, sublimation energy. And gaseous zinc is converted to the gaseous zinc ion by loss of 2 electron. This gaseous zinc ion is now aquated, undergo aquation, and forming aquated zinc 2 plus ion. Energy here during this energy release, therefore it is negative. And net reaction is now zinc plus aqueous forming zinc 2. So this is the net Q1 is the, so after this here net energy is here Q1. And similarly for the second half reaction, copper solid is converted to gaseous copper converted to Cu2 plus ion by the loss of 2 electron. Here again now undergo aquation forming this aquated Cu2 plus. These are the energies, and net reaction, and for this case Q2 is a plus 0.9 kJ per mole. Therefore total energy change in during the reaction is given by, so delta H0 equals to Q1 minus Q2 equals to minus 150 minus 59 equals to minus 209 kilojoule per mole, or we can write in a joule per mole in this way. Since the entropy change is not significant, we can write delta G0 equal to delta entropy delta G0 and is not significant, therefore delta G0 equal to delta H0. So delta G0 equals to minus F E0. Putting the value here, this value is this much, and E0 equals to, now we can calculate 20900 this value after putting, and value is coming 1.09 volt. 1.09 volt, and actually this is the value of this redox reaction, and here and this value E0 equals to 1.09 volt is a calculated value, and here in this case the experimental value is a 1.10 volt, which is very close to the calculated value, and therefore this is calculated value for this redox E0 1.09, and actual value is 1.10. Both the values are very close, therefore in this way which is so very close. So in this way, this is the method of calculation of redox potential of the redox reaction by using redox cycle. So this is one example of copper and zinc. And next part of this is the redox stability in water. This is very important, and so question can be asked here. So redox stability in the water can be explained in terms of, what is meant by the redox stability? So the stability of an ion or molecule in the solution is not inherent property, but depends upon the solvent as also in other solute, including oxygen that may be present in the solution. This is because ion or the molecule may be destroyed by oxidation or reduction, and which is brought about by the solvent or by the other species present. When water is used as a solvent, then it may affect the stability due to the four regions. So if the solvent is a water, then these are the four regions that it affects the stability. Water oxidizes the species and liberating the hydrogen gas. Water also reduces the species and liberated the oxygen gas. Water can make it undergo disproportionation, and atmospheric oxygen can also oxidize the species in the solution. So these are the four reasons. Because of that, so the solvent also affect the stability field. So we have to see the redox stability in water. So by using water, what are the stability, redox stability? So now here we are going to see the details about that, and one by one we are going to discuss in detail about this redox stability in the water. So first part is the water as a oxidizing agent. In many reaction, water is used as a solvent and water acts as a oxidizing agent. And in this case, in some cases it is oxidized by water, and oxidation state of that species increases while the oxidation state of hydrogen decreases in water. Consider the metal coming in contact with the water. If it undergo oxidation, liberating hydrogen gas, oxidation state of metal increases while that of hydrogen decreases. The reaction can be shown here. So metal plus water, whatever the metal is there, this is the metal, M for metal, water reaction forming this M plus ion, aqueous M plus ion, and here is the liberation of hydrogen gas and OH minus. So this metal and OH H plus ion, also we can express it same here, water from H plus from the water and forming this type of hydrogen gas and the metal ion. So this reaction can be predicted, also can be shown. Feasibility of this reaction is constructing, and cell is represented metal oxidized to metal ion, and here H plus ion reduces to hydrogen gas. So this is the one half reaction, this is another half reaction, and these two lines indicate the salt bridge which are connecting the two solutions. If the cell EMF is zero cell is positive under given condition, the concentration of ion, the reaction is feasible. If we can predict that metal gets oxidized by water, and here one example is considering here that scandium is oxidized to scandium 3 plus H, and here if we react scandium metal ion with the H plus ion forming scandium 3 plus ion and liberating the hydrogen gas. This is an example. During this reaction, the reaction is spontaneous because evolution of hydrogen gas is much slower and require quite higher concentration of H plus due to the hydrogen hole voltage. This is one that in this reaction water is act as an oxidizing agent, and so this reaction can take place, and in which water as an oxidizing agent. Another second point is also important, that water as a reducing agent. So water can also act as a reducing agent as well, because some species is reduced by water. The oxidation state of the species decreases while the oxidation state of oxygen increases in the water. For example, cobalt 3 plus can be reduced to cobalt 2 plus by water liberating the oxygen. The reaction shown here, cobalt 3 plus when react with the water, forming cobalt 2 plus and H plus and oxygen. So here this water reduces cobalt 3 plus to cobalt 2 plus. Oxidation number decreases means reduction is there, so it reduces. So it is a reducing agent, and cobalt is 3 plus reduces to cobalt 2 plus, and so this is the reaction. And standard reduction potential of cobalt 3 plus and H plus ions are 1.82 volt and 1.23 volt. Hence the EMF of the cell become E0 equal to 1.82 minus 1.23. So it is coming out to be 0.59 volt. Since the value is positive, reaction is spontaneous. So the reduction of cobalt 3 plus take place in water. So we can say that cobalt 3 plus cannot be used as oxidizing agent in the aqueous solution. And some other example is also there, that is reagent like dichromate, ceric solution, etc. can also be used as an oxidizing agent. So but here water acts as a reducing agent and reduces cobalt 3 plus to cobalt 2 plus. So and third point is also there. So the stability of the species in water is determined by the redox potential of the species and pH of the water. When graph the potential versus pH is plotted, the region where any species survive is called the stability field of water, shown here by the dotted line in the curve. So this is the stability field of water shown in the figure. So in the next part, so stability field of water here, in case of this, if water undergoes oxidation, the reaction shown here. So reaction is water is a liquid, undergo oxidation, and there is a loss of electron and forming to H plus ion and half oxygen. For this reaction, the Nernst equation can be written as E equal to E0 0.5059 upon 2 log product upon reactant. So this is product and this is the reactant. So here log water is 0, so the product upon the reactant, so concentration of water is 0, negligible, and after putting the value 1.229 here and putting the values of this log H plus, and here value is coming to be, this is H plus and this is the minus log is the pH, and E equal to this value is coming. So since log H plus is the pH and here oxygen is 1 atmosphere, so putting all this value we obtain E equal to 1.229 minus 0.059 pH. So by using this equation and on the basis of this equation, we can conclude that some important point. This equation is a straight line of the form of y equal to c plus mx. So as we know the equation of the straight line, y equal to c plus mx, where y equal to EMF and c equals to 1.229 volt, m equals to minus 0.059 and x is equals to pH. So this is the straight line with y equal to intercept 1.229 volt and having negative slope. This equation shows that the EMF of this couple depends upon the pH of the solution. This line gives upper boundary of stability field of water, and any species having higher potential than this can oxidize water with evolution of oxygen gas. The line shown in the graph AB, this equation does not consider the oxygen over potential, which in fact depends upon the electrode and electrolyte. This potential further increases due to oxygen over potential, as shown by the dotted line above the AB line. Similarly, this is the in case of half potential. Now the reduction of water to hydrogen can be shown, and it is shown in the next slide. This is the stability field of water, and H plus ion takes electron and become, so it is not shown, but now here this is the stability field of water for the hydrogen. H plus ion accept electron and forming half hydrogen gas. For this reaction, Nernst equation shown in this slide, and in this case E equal to E0, this is the Nernst equation, and in this equation E equals 0.059 upon 1 log H plus upon H2. So in this case, after putting this value, element, it is element, therefore 0, standard potential 0.059 log H plus minus this 0, and we have to separate these two, and after putting the value, pressure of hydrogen is 1 atmosphere, minus log H plus is the pH, so putting here the value pH, so we obtain this minus 0.059 pH and E equals to, so from this also equation we can have some conclusion, and important point from this equation is that this is also equation of straight line of the form y equal to mx, where y is EMF in the volt, slope is equals to m equals to minus 0.059 and x is equals to pH. This straight line passes through the origin and has negative slope. It can be seen that the slope is equal to that of line AB, and so it is a parallel to line AB. With increase in pH, the potential goes on decreasing. This gives the lower boundary of the stability field of water. Any substance having lower potential than this can reduce water to hydrogen. For example, alkali metal like sodium, potassium react with the water, liberate hydrogen. This line represents as a CD in the figure. This equation does not consider the oxygen over potential, which in fact depends upon the electrode and electrolyte. This potential further decreases due to the hydrogen over potential, as shown by the dotted line below the CD curve. In natural occurring system like ponds, lake, river, well, the normal pH conditions are between 4 to 9. Hence, two vertical lines as shown in this shown at this pH, the field between these two four lines is called the stability field of water. The vertical lines are there, and the dotted shaded line is known as the stability field of water in the figure. So this is the real stability field of water, and sometimes disproportionation in water can also take place. So disproportionation is defined as the reaction in which some ions or molecule is oxidized while other ions or molecule of the same species is reduced. Both are taking place simultaneously. The oxidation number of the species is raised or lowered simultaneously. In this process, transfer of electron takes place between the two molecule or atom or ion of the same species. And in other words, we can say that element undergoing disproportionation act as its own oxidizing and reducing agent. So only one same species undergo oxidation or reduction. For example, if you take the example, if we put the small amount of colorless cuprous sulfate in water, the solution turns blue due to formation of Cu2+, while brown precipitate is obtained due to the formation of metallic copper. And the reaction is shown here. So here, this is the reaction we show. This is the colorless Cu+, and after dissolving in water, what is forming? Aqueous Cu2+ is a blue and copper metal is a brown in color. So this is the one example of disproportionation, and in this case one of the Cu+ ion act as a reducing agent while other oxidizing agent. The reaction involve the two redox couple with the potential shown in the next. Here it is shown, and a standard EMF for the disproportional reaction is also can be determined by E0 equal to potential of both. That is, two potentials are there. E0 Cu plus upon Cu equals to 0.52 volt, and the second is E0 Cu2 plus upon Cu plus equals to 0.15 volt. And difference between these two, we get the standard potential or standard EMF of that potential of that cell. Since potential is positive, the reaction is thermodynamically spontaneous. If you compare this this example of copper, the potential of this copper couple is positive, and therefore the thermodynamically the reaction is spontaneous. And last one point is also there, and that is when solution is exposed to the atmosphere, there is a possibility of reaction between the solute and the oxygen dissolved in the solvent as well as in the atmosphere. And for this case, we can consider the solution containing Fe2+, since the standard redox potential of Fe3+ oblique Fe2+ couple lies between the stability field of water, and it shows that Fe2+ should be stable in the water. This is actually in the case. However, it becomes different solution is exposed to air, because there is a now possibility of Fe2+ may get oxidized to Fe3+ by the atmospheric oxygen. And so here, for example, is shown here how it is taking place. So the reaction can be written as Fe2+ is oxidized to Fe3+. So it reacts with the oxygen. So oxygen pressure in the atmosphere is oxidized here, and oxidation is taking place. So EMF of this reaction is can be obtained by combining the two reactions. And here this is another. And for this potential is given Fe2+ gain 1 electron, Fe2+, and redox potential can be determined and by using the total reaction is given here. And from this we can say that the redox potential of the total reaction is given here, and in this case the potential is positive in acidic condition. There is a spontaneous conversion of Fe2+ to Fe3+ in the presence of atmospheric oxygen. It shows clearly or it explains clearly that Fe exists mainly in the form of Fe3 Fe3 oxidized in solid, and in Fe3 ionic form in solution as well as O's. So this Fe2+ converted to Fe3+ in the presence of atmospheric oxygen, and Fe exists mainly in the form of Fe3+ H oxide in the solid. So this is the oxidation of by atmospheric oxygen of Fe. So Fe2+ is converted to Fe3+, and the redox potential can also be calculated. So these are the different concepts in this case. So we have seen the analysis of a redox cycle, and that is calculation of redox potential by using a redox cycle. And also we have seen the example of copper and zinc, and after that we have seen the redox stability field of water. One figure is given, and in that figure the shaded part is the stability field of water above which the oxidation or reduction can take place. So there is the boundaries, and we have seen that water, when the reaction taking place in water, then water can act as a oxidizing agent. It can also act as a reducing agent, disproportionation reaction, and also the oxidation of Fe2 to Fe3 can take place by the presence of oxygen in the atmosphere. So these are the different reactions of redox reaction, and calculation of redox potential and stability field of water we have seen in today's presentation.